Okay, so for this video, I'm going to take y to be a binomial random variable with n trials and p probability of success, and I want to prove that the expected value of y is n times p. The variance of y, I'll suggest how this is proven, it has a similar idea in it, is actually n times p times q. Okay, and we are going to use a result from your exam about combinations, this one here, that y times n choose y equals n times n minus 1 choose y minus 1. So to start this proof, we're just going to start with the definition of expected value. So the expected value of y is equal to the sum for discrete random variable of y times the probability of y over all values of y. Because we know y is a binomial random variable, we can now plug in the probability of each y. So the probability of a specific value y is going to be n choose y, p to the y, q to the n minus y. And for this binomial, there's n trials. So y is going to go over, assume the value is 0 up to a maximum of n. Okay, so there's one simplification we can make right now that will help later on. So notice that in this term, I have y times a bunch of other stuff. When y is equal to 0, y times a bunch of other stuff is 0 times a bunch of other stuff. So y equals 0 just generates a term that is 0 in this summation. So I'm actually going to change my lower summation limit on my summation to y equals 1 is where I'll start summing. Okay, the next thing I'm going to do is I am going to use this identity for combinations that you guys had from exam 2 to simplify what I have in my summation. And the general strategy of what I'm doing with this summation is I'm going to try to convert this sum into a sum of a bunch of related binomial probabilities over all the trials. And if you sum all the probabilities in a binomial probability distribution, you should get 1. So that's a strategy that can sometimes help you with these summations to get a really nice closed form that doesn't involve a summation in it. Okay, so that means that this component y times n choose y, I can substitute using the identity and make it into n, this n times n minus 1 choose y minus 1. Okay, and making that substitution, I am going to get the sum from y equals 1 to n of, instead of y times n choose y, I get n times n minus 1 choose y minus 1 times p to the y times q to the n minus y. And because this n, this multiplicative constant, doesn't depend on y, I can pull it out of the summation. So in the next line, I'm going to get the sum y equals 1 to n. The n goes out front. N times n minus 1, choose y minus 1, p to the y, q to the n minus y. Actually, I made a little mistake up there. That should have said n minus y. Okay, so I'm getting a little bit closer, and I still want to make this into binomial probabilities. Want the form to be for binomial probabilities with n minus 1 trials and probability p of success. And I want this to be the probability that y equals y minus 1. Okay, so I almost have that, but notice here the exponent on p should be y minus 1. So I'm going to break p to the y down into p to the y minus 1 times p. And actually the exponent on q is just fine because it should be n minus 1 minus y minus 1, and the ones drop out. Okay, so I'll write that out a little more specifically. So I'm going to get n times the sum of y equals 1 to n minus 1 choose y minus 1, p to the y minus 1 times p, and I'm going to rewrite q to the n minus y just for clarity as q to the n minus 1 minus y minus 1. Okay, so that quantity is the same because the negative 1 drops out with the minus the negative 1, so it's still the same as n minus y that we originally had, but it's just in a form that is going to help us later on. Okay, so I'm going to pull the p out of the summation, and we know what we're trying to prove, the expected value is n times p. So you might suspect that that summation should somehow sum to 1. So let me try to convince you of that. So next we're going to get the sum, the n times p comes out front, times the sum from y equals 1 to n of n minus 1, choose y minus 1, times p to the y minus 1, times q to the n minus 1 minus y minus 1. And if you look at what we're summing really carefully, you'll recognize that it's summing from 0 to n minus 1, all the binomials in a binomial with n minus 1 trials and p probability of success. But let me re-index to make it really clear that that's what's going on. So let's re-index and let k equal y minus 1. Okay, if I do that re-indexing, I'm going to get still the n times p here, the sum. Okay, before we had y equals 1, but if y is 1, then k is 1 minus 1 or k is 0. So k equals 0. For the upper limit, before I had y equals n, so k is going to be n minus 1. So sum k equals 0 to n minus 1. And then I'm going to have n minus 1, and instead of y minus 1, I'm going to put k, because I'm substituting. And p to the y minus 1 becomes p to the k, and this last factor becomes q to the n minus 1 minus k. Okay, so hopefully now it's easier to recognize this summation as the sum of all the binomial probabilities. If the number of trials is equal to n minus 1, and p is the probability of success. So notice we need a sum from 0 to n minus 1. That's actually what we're doing. And this is what the binomial distribution would look like for the probability y equals k. So that entire summation becomes 1. And so I'm going to get n times p times 1, which is just np. Okay, so to prove the variance formula, you can use a very similar trick. The variance, because of that combinations, to prove the variance of y is n times p times q. You want to look at the variance as the expected value of y squared minus the expected value of y, that whole quantity squared. So we already know expected value of y is n times p squared. So that part's not too hard. The expected value of y squared is the part that's a little bit harder. So if we go at that directly, things don't cancel out quite right. y squared times n choose y, p to the y, q to the n minus y. So we will get one y canceling with a y here, but then you're left with another y. So an easier way is to start by calculating the expected value of y times y minus 1. And then you'll have the cancellations that really work in your favor. So that'd be y times y minus 1 times n choose y, p to the y, q to the n minus 1. And then when you break this combination down into n factorial over y factorial times n minus y factorial, inside this y factorial you have a y times y minus 1. So that will cancel with some of these. And then you can again manipulate the summation into being a sum of a bunch of binomial probabilities. Okay, there's a little bit more work because this is not expected value of y squared. It's the expected value of y squared minus y. But you know e of y, so it's e of y squared minus e of y. E of y is n times p, so it will work you around to what the expected value of y squared is.